So since we have clarified all these things, and now it's time to talk about the contents of the stress-energy-momentum tensor. And we sort of describe the content from the point of view of an observer. There are a couple of vectors associated with the observer, and our job is to plug those vectors in here and then attach a meaning, right? Because the tensor T, which is the stress tensor, is indeed a geometric object. So anytime we want to probe a geometric object, we have to do it from the point of view of an observer. And of course, the object itself doesn't change as a whole, but different observers will observe it differently. So this is what we do. We insert some vectors in these two places, and that will tell us about the content from the point of view of an observer. And then we can generalize that by saying that all the other observers will observe similar things from their point of view, right? The way we deal with all other topics in relativity. So the first thing we will be plugging in here is the full velocity of an observer. So I can plug it in here. So U denotes the U is a vector that denotes the forward velocity of an observer. Right? So I can plug it in the first slot, or I can plug it in the second slot, and it doesn't matter. And it doesn't matter because the stress tensor, or stress energy momentum tensor, or SEM tensor, is symmetric in both of its indices. So it doesn't matter at which slot I plug in the forward velocity of the observer. And what is this going to tell us? This is going to tell us the negative of momentum density, right? Negative of momentum density. So here V denotes the volume. So differentiating with respect to V gives us the density, and P is the momentum vector. So V is the volume, which will be 3 volume to be precise, and P is a 4 vector, right? So obviously, the 3 volume in 4 dimension will also depend on the observer, and therefore this whole thing will be measured with respect to the observer whose full velocity is U. We can also write this in the component form. So this would be, in terms of the component, I would write it as T alpha and then beta and then U beta. I could have also written as T alpha and then beta, U beta. This is to emphasize the symmetric nature of the stress-energy-momentum tensor. And this is, of course, going to be the negative momentum density. Now, I have to be honest with you. This is what's been written in the book, and the book that I've been following has been written by Misner, Thorne, and the great physicist Wheeler. They have been consistent a lot of the cases, and in some places there is a bit of inconsistency, which is not major, by the way. The content is still correct, but this is just to be very, very precise. By the way, those differences or small inconsistencies doesn't make any difference whatsoever in terms of physics, but to people who are wants to be very correct, or if there is anyone who studied mathematics or are interested in relativity from a mathematical point of view, then they would like to disagree with the notations here. So for example, I have called it a 4 vector, right? And I have called this one a 0 to tensor, but notice I have made one of the elements contravariant and the other element covariant, or one upper index and another lower index. which is not really the characteristic of the components of a 0-2 tensor. So what's going on here? So if I have to be truly consistent, what I should have done is, instead of writing the momentum vector or momentum 4 vector here, I should have written a momentum form, which is the flat operation carried out on the 4 momentum vector that gives us associated momentum 1 form. So then I should have also made a correction here where I would have got a momentum 1 form, or the component of momentum 1 form, and similarly I could have written T alpha beta both lower indices, and here T alpha beta both lower indices. Of course, then everything would be truly consistent. But in terms of the physical content of this lecture or video, it doesn't make any difference. So I think it is pretty clear. If you plug in the full velocity of an observer at any of the spots, it doesn't matter which spot, because the stress-energy tensor is symmetric in both of its slots. That will give you the momentum density observed, right, with respect to that observer. It's actually the negative momentum density with respect to that observer. This is the 3 volume with respect to that observer, 3 volume of the place that we are interested in, and of course this is the projection of momentum from the point of view of that observer. So this is the first thing. T tells us the momentum density when we plug in the full velocity of an observer. So that's number 1, right? Let's go to number 2. So in the first point, we have talked about what this object is. In the second point, we will be inserting another vector into the remaining slot, or it could as well be written, because of the symmetry that is afforded by the stress tensor, we could have just plugged in U in the first slot, and in the second slot we plug in another vector. And let n be a unit vector, right? Unit vector, which is otherwise arbitrary. So unit vector, but this is an arbitrary unit vector. Arbitrary unit vector, right? So let's plug that in here, or here. They are equivalent. And what does this give us? This gives us, so when the full velocity is inserted, we remember that this gave us this, right? dp dv, right? With respect to this observer. But now if we insert another vector, another arbitrary unit vector, then this gives us the projection of momentum density observed by that observer. So this is the component, or the projection. So this is the projection of the full momentum density of momentum density along that direction n, right? So plug in the full velocity of an observer, it gives us the momentum density, or the negative momentum density with respect to that observer. In the remaining slot, plug in an arbitrary unit vector, and that will give you the projection of the momentum density along that direction of the unit vector, right? So that's point number 2. Let's go on to point number 3. Point number 3 is an interesting one. So this time, in the 2 slots of the stress tensor, two slots where we can plug in two vectors, we are going to plug in this one vector, which is the full velocity of an observer. So in both of these places, we plug in the full velocities. What does that give us? So obviously, in terms of component, this is going to give us T alpha beta, then U alpha, U beta. And the meaning of this is very, very straightforward. And that is the mass energy density. Of course, mass energy density means mass and energy content per unit volume, but we know that density is not a geometric object. It is observer dependent, and so this is mass energy density with respect to our observer, whose full velocity is u, right? So with respect to the u observer. So this was very straightforward. Let's go on to point number 4, which is going to be the last one. To illustrate this point number 4, we take an observer. That's given. So pick an observer. And what we do is that we take two space-like vectors in the Lorentz frame of the observer. So from the point of view of that observer, his unit vector along the time axis is going to be the time-like vector, and he can take 3 basis vectors. It's almost impossible to draw 4 basis vectors in 2 dimension. So this is how we are going to describe it. So let's assume this is some other dimension, right? We don't have to worry about it. So the observer in 4 dimension can choose one time-like unit vector, which is denoted by E0, but he can also choose 3 mutually orthogonal, they can be, but they don't have to be orthogonal, by the way, but they have to be independent. He can choose 3 independent basis vectors, so E1, E2, and E3, that's how we denote them. And we need to take 2 of those, and it can be any 2. So just pick EI, right, and EJ, right? So denote any 2 basis vectors, which are space-like, by the way. So space-like basis vectors, right? And we'll take the geometric object T, which we are interested in, and it has 2 slots, as we know, as we have been using them. And in the 2 slots where we can plug in 2 vectors, we'll plug in these basis vectors, so I, E, J. So in the 2 slots, we plug in these 2 space-like basis vectors, but it doesn't matter in which slot we plug in EJ or in which slot we plug in EI, right, because of the symmetry, which is kind of obvious at this point because I spoke about it so many times. And this is going to give us the components, the ijth component or the jith component of this stress tensor. But what does it mean, right? That's what we are interested in. So since this is the space-like basis vectors, and remember we told you about the momentum density and mass energy density and stress. These 3 important contents are encoded in the stress tensor. This is the space-like part, so this means this would represent stress. And I presume that you are familiar with the stress tensor. That stems from the study of elasticity. So to be precise, this is what it means, right? So it means assume at any point, right? So this is some sort of point, and let's assume this point resides on the coordinate lines of xi, right? So this is the point that we are interested in. This is denoted by xi. So we go a little bit to the left, which is denoted by xi minus epsilon. This is the distance, which is epsilon. And we go a little bit to the right, which is xi plus epsilon. So a bit to the left, a bit to the right. And this gives us a surface to work on. Because remember, we are talking about the space-like part of the tensor. And we can assume there is also an associated surface, and on this surface some sort of force is acting upon, right? And the same can be told about this surface as well, right? So perhaps in this direction, right? And the difference in those two forces gives us the amount of force that acts from one side to the other, right? Now that force is going to be a geometric object, but so it would have components, and we are interested in the component that acts along xj. Or it could be the other way around. We could have constructed this whole process on the coordinate line of xj, and then the force that we are interested in, we could have taken the xith component of the force, right? And not only the force, but the force across the unit surface area. So if these surface areas are unit, or we could have just divided that component of the force. So the force, the jth component of the force, right, working perpendicular to the area along xi, and then we calculate the not just the force, but force per unit area, that is precisely what stress is. That is the definition of the stress. Stress is indeed the force per unit area. It depends on the component you take and the surface on which it works on. That is stress, right? That is stress. So these components here, they tell us about the stress. So notice that we have got all the contents that we are looking for. We have got mass energy density with respect to an observer. We have got the stress acting on a point with respect to an observer. And we've got the momentum density with respect to an observer. So altogether, stress-energy-momentum tensor encodes all of the mass and energy content and the stress and the momentum content into a single geometric object. And that object is called the stress-energy-momentum tensor. In the next video, we'll be looking at an example which is very important for the discussion of stress-energy-momentum tensor in many circumstances, and will come in handy in future when studying general relativity, the solution to different settings, and especially in the context of cosmology.